Let's consider another important catalytic reaction, the synthesis of ammonia from nitrogen and hydrogen. So here's our overall reaction, N2 plus 3 H2 going to 2 molecules of ammonia. Unlike our previous example of CO oxidation in catalytic converters, in practice this reaction often operates close to thermodynamic equilibrium. In the next video, we'll see how we can express the rate of the reaction in terms of an approach to equilibrium. So let's assume that the ammonia synthesis reaction proceeds by the following sequence of elementary steps. So we'll have dissociative adsorption of nitrogen, dissociative adsorption of hydrogen, and then sequential hydrogenations of our nitrogen species through Langmuir-Hinshelwood type reactions with bound hydrogen to form NH, followed by NH2, followed by NH3, which desorbs from the surface of the catalyst. So since step 1 involves dissociation of a very strong nitrogen-nitrogen triple bond, let's assume that this is our sole rate determining step and that all the other steps are quasi-equilibrated. So we can write the stoichiometric numbers for each one of these steps. So essentially to complete one catalytic cycle, how many times each step has to occur. So for step 1, it's just once to form our 2 adsorbed nitrogen atoms. Step 2 will need to occur 3 times, and then all other steps will need to occur twice. So we can write our overall rate as the rate of step 1. So writing this as a turnover rate, it'll just be the forward rate constant times the pressure of nitrogen times the coverage of free sites squared minus the reverse rate, which is a reaction rate constant K minus 1 times the coverage of adsorbed nitrogen squared. So we can find an expression for our vacant site coverage in terms of measurable quantities from a site balance. So we'll write this site balance in terms of coverages. So we can write 1 is equal to our coverage of vacant sites plus each one of our adsorbates. So here we'll have adsorbed hydrogen, adsorbed nitrogen atoms, adsorbed NH, NH2, and NH3. So we can express the coverage of each adsorbate as a function of the vacant site coverage, such that this is the only independent variable in our site balance. And we can do this since steps 2 through 6 are quasi-equilibrated. So we can begin by setting up an expression for our coverage of hydrogen atoms based on the quasi-equilibrated step 2. So we can write the equilibrium constant for hydrogen adsorption times its partial pressure times the vacant site coverage squared is equal to the coverage of hydrogen atoms squared. So now we have an expression for our coverage of hydrogen in terms of an equilibrium constant for adsorption, a pressure, and the coverage of vacant sites. So since steps 3 through 5 involve multiple adsorbates, it's easiest here to start with step 6 and solve for the ammonia coverage and then work our way up to the other nitrogen containing intermediates. So we can write that the equilibrium constant for step 6 times the coverage of ammonia is equal to the pressure of ammonia times the coverage of vacant sites. So here we can simply express the coverage of ammonia as its partial pressure divided by the equilibrium constant for step 6 times the free site coverage. So for step 5, we can write that the equilibrium constant, K5, times the coverage of NH2 times the coverage of H is equal to the coverage of ammonia times the coverage of free sites. So we can write that the coverage of NH2 is equal to the coverage of ammonia divided by the coverage of hydrogen times the equilibrium constant K5 times the free site coverage. So we'll have a similar expression for our steps 3 and 4 since we are sequentially adding one hydrogen atom to our nitrogen bound species in each one of these steps. So we can rewrite this expression for the coverage of NH2 using our expressions for the coverage of hydrogen and the coverage of ammonia. So this will come out to the pressure of ammonia divided by K2, that equilibrium constant for hydrogen adsorption, to the 1/2 times the pressure of hydrogen to the 1/2 times the equilibrium constants for steps 5 and 6, all times the coverage of vacant sites. So here this is a expression that we can insert into our site balance eventually. Okay, so doing the same for step 4, we can write that the equilibrium constant for step 4 times the coverage of NH times the coverage of H is equal to coverage of NH2 times the coverage of vacant sites. So this is going to look quite similar to our expression for step 5, and again step 3 will look very similar since chemically all of these steps are very similar where we're adding one hydrogen atom to this nitrogen containing adsorbate. So solving for the coverage of NH, we can write that this is equal to the coverage of NH2 divided by the equilibrium constant K4 times the coverage of hydrogen, all times the coverage of vacant sites. So now we can insert our expressions for the coverage of NH2 and the coverage of hydrogen. So when we do this, we can write this expression as our numerator is just the pressure of ammonia. Our denominator here becomes the equilibrium constant for hydrogen adsorption, K2, times its partial pressure, times the equilibrium constants for K4, K5, and K6, times the vacant site coverage. So finally for step 3, again this will look very familiar now. We'll have equilibrium constant K3 times the coverage of N times the coverage of hydrogen is equal to the coverage of NH times the coverage of vacant sites. Solving for the coverage of N, this will be coverage of NH divided by equilibrium constant K3 times the coverage of hydrogen, all times the vacant site coverage. So inserting our expressions for the coverage of NH and the coverage of hydrogen, we can get this all in terms of measurable quantities and the vacant site coverage. So our numerator will be the partial pressure of ammonia. Our denominator will now become K2 to the 3/2, pH2 to the 3/2, and then the equilibrium constants for steps 3, 4, 5, and 6. And this will all be multiplied by the free site coverage theta star. So now we've expressed the coverage of each one of our adsorbates as a function of the vacant site coverage, so we can insert all of these expressions into our overall site balance to get an equation that just has one independent variable, the free site coverage. So if we insert these all into our site balance, factor the vacant site coverage out, and solve for it, we'll get an expression that looks like this. 1 over terms associated with theta star divided by theta star plus that of hydrogen over theta star plus that of NH2 over theta star plus that of NH, N, and finally ammonia. And so now we've come up with expressions for each one of those terms. So skipping forward, I'll just show you the overall expression since it's a little bit cumbersome. So here's our final expression, and so this term is associated with the vacant site coverage divided by the vacant site coverage. Here's our coverage of hydrogen divided by the vacant site coverage. This is our expression for NH2, NH, N, and then finally for ammonia. So we can again write the rate, the overall rate of ammonia synthesis as the rate of step 1, that reversible nitrogen dissociative adsorption. So that's going to be equal to our forward rate constant K1 times the pressure of nitrogen times the free site coverage squared minus the reverse rate, so that's K minus 1, times the coverage of N squared. So we can rewrite this a little bit differently. So we can factor out K1 times the pressure of nitrogen times the vacant site coverage squared times 1 minus theta n squared over theta star squared times 1 over the equilibrium constant for step 1, K1, times the pressure of nitrogen. So we can write out a final rate expression that the rate is equal to K1 times the pressure of nitrogen times the vacant site coverage squared times 1 minus the pressure of ammonia squared, so that's our product, divided by the pressure of nitrogen times the pressure of hydrogen cubed times 1 over the series of equilibrium constants, K1, K2 cubed, K3 squared, K4 squared, K5 squared, times K6 squared. So all of this was obtained by plugging in our expression for the coverage of adsorbed nitrogen atoms divided by the vacant site coverage. And so this is our final rate expression. This is all in terms of measurable quantities, and we have an expression for the vacant site coverage in terms of measurable quantities. And so in the next video, we'll talk about how we can express this term on the right side of our equation in terms of the approach to equilibrium of the overall reaction.